Okay, so we're going to talk about writing, graphing, and interpreting a piecewise function. So sometimes a function may need more than one formula or equation to accurately model a real-life situation. For example, taxi fares, right? You have a certain price for 0 to 10 miles, and then the way that price is calculated changes if you go further than 10 miles, something like that. The U.S. federal tax code, right? You get charged a certain percentage of your income when you make below, like, I think it's $3,000, and then between 3,000 and I don't know what the cutoffs are, but 3,000 to some other amount, you get charged a different amount. So we need different formulas for different incomes to determine what you owe for taxes. Scales that classify tornadoes or late fee charges for credit cards all require a function that uses more than one formula to model it. So in these situations, the function is defined on pieces of the domain. So that's why we call it a piecewise function. So you break up the domain into pieces, and you have a different formula for each piece of the domain. So here's sort of a simple function. The graph shows the amount of water in thousands of gallons in a swimming pool after T hours have elapsed. So how has the water in the pool changed over the interval T equals 0 to T equals 50? What's happening to the water level in this pool? At first it's increasing, right? And then it levels off for a little while, and then it decreases down to 0, right? So we were filling the pool up, it stayed full for a while, and then we drained the pool. Okay, so we have, on what interval is the water level in the pool increasing? 0 to 20, right? Remember, you always give the X interval to explain where something is increasing, or T in this case. Okay, so it's increasing from 0 to 20. And remember, when we describe increasing and decreasing, we always use the round brackets, because right at the end points, it's kind of doing neither increasing nor decreasing. All right, on what interval is the water level constant? 20 to 30. Time 20 hours to time 30 hours. The level of water in the pool was constant. And then over what interval is the water level decreasing? 30 to 50. Hour 30 to hour 50, the water level is decreasing. So these three intervals, 0 to 20, 20 to 30, and 30 to 50, they define the three different pieces of the domain for our piecewise function. Three different things are happening. We're going to have to use three different formulas to describe what's happening in those three intervals. So we represent the pool problem by writing the number of gallons G as a function of the number of hours T using a piecewise function. So we have, this piece has a formula. It's a line. So in a previous class, I'm sure that you learned how to find the equation of a line. So this line is y equals 0.3 t plus 2. And I believe next class we're going to review how to find that. And then the equation of this line, that's y equals 8. And the equation of this line is y equals negative 0.4 t plus 20. So each of those lines has a different formula, and then the notation we use for a piecewise function is we write g of t, right? So capital G is representing the number of gallons in the tank at time t, and you put one big curly bracket equals one big curly bracket, and then you list the three different formulas, right? So we've got 0.3 t plus 2, 8, and negative 0.4 t plus 20. So we write down those three different formulas for the three different pieces. And then we put comma if, and we say what t values you use that formula for, right? So you would use the 0.3 t plus 2 only when t is between 0 and 20. So you write if 0 is less than or equal to t is less than or equal to 20. So when t is sandwiched between 0 and 20. And you use 8, the constant formula, when t is between 20 and 30. And you use the last line, negative 0.4 t plus 20, if when? Between 30 and 50. If 30 is less than t, less than or equal to 50. Now, where you put the or equal to part in this particular question doesn't really matter. Because if I plug 20 into the line 0.3t plus 2, I get 8. And if I plug 20 into the line y equals 8, I also get 8. So I could put the or equal to sign here or here. Either line would give me the same value for 20. But we typically don't put it in both places. It's not really wrong if you put it in both places. It's just kind of bad form. Okay, so you pick one or the other, right? We can put it here or here. And the same with the 30, because this line and this line both give you 8 when t is 30. So we could put the or equal to here, which is what I chose to do. Or you could put it here, but typically you don't put it in both places. No, when I say both, I mean not here and here, right? So because I could include the 20 in either line. I could have this line include 20 or this line include 20, and I'll get the same value of 8 right at 20. So we have an or equal to here or here. And then same thing for the 30. You'd have an or equal to here or here. And technically you could write both because they both give you the same value. It's just kind of bad form. We'll do several more examples. I think it'll get clear. So here's another real life example. My cell phone plan with Verizon charges $79 a month for 700 minutes, and any minutes over that allowance is charged 45 cents a minute. Should be a line there, 45 cents per minute. So we want to use a piecewise function to represent the monthly cost of my cell phone plan, where C is the cost and M is the number of monthly minutes used. So if I use less than 700 minutes, how much is my bill going to be? $79. So I'm going to have two different formulas. One if you use less than 700, one if you use more. So if I use less than 700 minutes, I just get charged $79. Okay. $79 if M is less than or equal to 700, because I think you can use up to 700 and you just get charged the $79. But if M is larger than 700, if I go over M greater than 700, how do I calculate my monthly bill? 79 plus, yeah, 0.45 times, do I get charged 45 cents a minute for every minute I talked? Only the number that were above 700. How do I calculate how many minutes more than 700 I used? Yeah. You got it. Take the number of minutes you talked, like say you talked 1,000 minutes, right? Take away your 700 because those 700 are included in your $79. So you're getting charged 45 cents a minute for just the 300 beyond 700 that you talked, right? So you just have to do 0.45 times M minus 700. So we just figure out how many over 700 we went by subtracting. And you use that formula if M is bigger than 700. So let's say I want to find the cost for 535 minutes. What is C of 535? $79. Right? It's under 700 minutes, so $79. So C of 535, if I were equals $79, if I were to interpret that, I would say it costs $79 to talk for 535 minutes. Okay, and then what would C of 850 be? Yeah, it's a linear equation. I'll have to plug 850 into the second formula here. Okay, so it is 79 plus 45 cents times 850 minus 700. So we get $146.50. So I'll write out what I typed in there. Plus 0.45 times 850 minus 700 is 150. So that comes out to 146.50. So I would write it costs $146.50 to talk for 850 minutes. Did I mess up? Let me see. Oh yeah, 850 minus 700 has to be all in parentheses. Yep. Okay, so let's graph a piecewise function. So the past two examples I gave you, one I gave you a graph and the other one I gave you a description, a verbal description. Both of them we wrote the formula. Now I'm giving you the formula and I'm going to draw the graph. Okay, so f of x equals x squared if x is less than 1, and f of x equals 1 minus x if x is bigger than or equal to 1. So with any formula, you can always go to plotting points, right, if you don't know how to graph it, even a piecewise formula. So let's start there. And maybe I'll do like -3, -2, -1, 0, 1, 2, 3. Just pick a few x values. We'll figure out the y values and plot them. So if x is -3, which formula do I use? The x squared or the 1 minus x? X squared, right? Because you use the first formula x squared when x is less than 1. -3 is less than 1, so I'm going to use the first formula. So -3 squared, that's 9. Why isn't it -9? Yes, because a negative times a negative is a positive. -3 squared means -3 times -3. Okay, -2. Should I use x squared or 1 minus x? X squared, so I get 4. -1, that's still less than 1, so I'm going to get 1 when I square it. 0 is less than 1, so I'm going to get 0 when I square it. What about when x equals 1? Which formula should I use? The second one, because you use the second formula when x is bigger than or equal to 1. So when I plug in a 1, x equals 1, so I use the second formula. And 1 minus 1 is 0. All right, when I plug in a 2, which formula should I use? The second one. 1 minus 2 is -1. And when I plug a 3 into the second formula, I get -2. So let's plot my points. So I have -3, 9, -2, 4, -1, 1, 0, 0, 1, 0, 2, -1, and 3, -2. So this guy looks like, when I'm to the left here, that looks like x squared. That's what x squared looks like. And this looks like a line, 1 minus x. but I don't have anything between 0 and 1 graphed. So which formula should I be using when I'm between 0 and 1? I heard it. Say it louder. X squared. Because numbers between 0 and 1 are less than 1, so I'd be using x squared. So just pretend you could put 1 into x squared. What do you get when you square 1? 1. So I would go all the way to that point, 1, 1, but I wouldn't include it because I can't actually put a 1 into x squared. But it looks like this. Follow the graph for x squared. That kind of makes sense? Here's another method that I really like. I'm going to erase all of this and we'll start again. So this is point plotting, right? So you can do it that way. Or if you know what y equals x squared looks like, or you can use GeoGebra or your graphing calculator to get a picture of y equals x squared, just graph x squared on its entire domain. So I'd have 0, 0, 1, 1, 2, 4, 3, 9, and same thing on the left. There's x squared. So I just graph the whole thing. Ignore these domain restrictions. And then in another color, I'm going to graph 1 minus x. That's a line. Its y-intercept is 1, and its slope is -1. So I could go down 1, right 1, get another point. There's my line. Graph the whole line. Different color. Then just decide which parts you want to keep and which parts you want to get rid of based on the domain restrictions. So x squared, I only keep the part of it that's to the left of 1. Erase everything else. And I'm not going to include the part at 1. So open circle there. Oops. All right, and then for the line, I'm only going to keep the part that's to the right of 1. So I got to erase all this stuff to the left. It's a little tricky with my smartboard eraser, but. So that's the end result. Make sense? Okay. All right, one more example of a piecewise defined function is the greatest integer function. It's a common piecewise function used in mathematics, and it's denoted with these little brackets here. Also, sometimes like this, little feet. And it basically means round down. Okay, it says the greatest integer that is less than or equal to x. So the biggest number that is smaller than the input. So round down. Okay. So for example, if I took 2 and rounded down to the integer below, well, you don't have to round it at all, right? So it's 2. Right. Then you take your 2.6, round down to the integer below, 2. And 2.9, round down, 2. 2.99999, 2. So no matter what you plug in, 2 point anything, the greatest integer that's less than or equal to it would be 2. So consider this the round down function. So we're not using the standard rounding rules of, 0.5 and above round up, below 0.5 round down. It's just always round down. All right, so the greatest integer greater than or equal to 3 is 3. What is the largest integer less than or equal to 3.6? 3. And round down 3.9, you get 3. Yes. It's just, these are two different ways of saying the same thing. So if I write int of x or these brackety things, they mean the same thing. So notice how you jump from 2 to 3 in the function values, right? So my input 2, 2.6, 2.9, 2.9999999, those all give outputs of 2, and then we make a jump. When you go to 3, an input of 3, you start getting outputs of 3. And the jump happens at 3. Okay, what do you think the greatest integer that is smaller than negative 2.3? You round a negative 2.3 down. Where does it go? Negative 3. Yeah. Because if negative 2 is actually bigger than negative 2.3, so to round it down, we'd have to go down to negative 3. What about if I took negative 0.3 and rounded down? Where would I end up? Negative 1. Got it. Okay, so let's try to sketch a graph of this greatest integer function. So for x's between negative 3 and negative 2, negative 2 point somethings, my output is going to be negative 3. Any x, any negative 2 point something, will give you negative 3 as the output. How about negative 1 point somethings? What would I get? Nope. Negative 2. And negative point somethings? Negative 1. What about numbers between 0 and 1? If I round them down, where do I land? 0. Numbers between 1 and 2, round them down, you land at 1. 2 to 3, round down, you get 2. 3 to 4, round down, you get 3. Okay, so let's graph this. So at negative 3, if I were to plug in a negative 3, I get negative 3. And I get negative 3 for every x value in between there until negative 2, right? But not when I plug in a negative 2. When I plug in negative 2, I get negative 2 because no rounding is necessary. And then between negative 2 and negative 1, I always get negative 2. And then between negative 1 and 0, when x is between negative 1 and 0, I get negative 1. Between 0 and 1, I get 0. Y is 0. And then I just keep building this staircase. So that's a picture of the greatest integer function. This is an example of something we call a step function. Okay. All right, so I have several real examples of places where you would find piecewise functions, and I'm going to have you work in your groups to sketch a graph and write an equation of each of these. And whichever one feels more natural to you to do first, go ahead and do that. Some people like to draw the picture first and then use that to write a formula. Some people like to write a formula and then use that to draw their picture.